I got drawn in on sort of into the subject about what happens after the fire, and I just want to share some experience with you.
I learn so much by talking to other people that I meet, and I make really long-standing connections.
Pouring water onto an EV in thermal runaway is like pouring water onto the roof of your house when your kitchen's on fire. Thank you, gentlemen.
Good morning, everyone. I'll thank you, Charles, for not stealing all my slides and only the first one. So I work with a manufacturer called Siderise, and after yesterday, I think we're sort of the villains in Who Set the World on Fire. So I'll try to do justice, and I think we do justice, at least we do try to do the right thing in the world. And I'll talk about passive fire protection in external facades. Yeah. So we're going to be talking about external cladding and curtain wall solutions. Oh. Thank you so much. I appreciate that. So we'll talk about external cladding solutions and curtain walls and fire solutions for them specifically. So first up, we look at some curtain wall solutions. So what is curtain wall? Just for novices, it's basically a bunch of mullions and transoms which are made from non-fire rated aluminum and non-fire rated glass. It's so that you can see the beautiful sun when it shines, which is occasional, first of all. So when it does, you want to see it in its might. So that's where curtain walls are used. It's usually continuous curtain walls that are a fire risk or a hazard, and that's where you have non-fire-rated glaze used in your spandrel construction, which covers your floor slab and your services that run below your floor. So why is this a fire risk or a fire hazard? So, like I mentioned, curtain walls are made from non-fire-rated aluminum, which lose its structural integrity at roughly 350 degrees Celsius. At this basically temperature, aluminum profiles will also buckle, lose its structural integrity. The glass is going to have its thermal shock behavior, which is going to crack and fall as well. So what are the fire risks or fire hazards which you have in a curtain wall construction? The first one is an internal fire spread, which is through your gap between your floor slab and your curtain wall. So this gap is present to accommodate the movement of your curtain wall, and this gap is can have something called as an internal fire spread. So you usually have curtain wall fire stops, if it makes sense, or perimeter barriers as it's usually called in that specific location. This will accommodate for the movement of your fire stop and also perform in a fire scenario. You have another fire hazard called as a leapfrog effect. Now this leapfrog effect, it's basically fire breaking your external vision panel, traveling above your spandrel panel and entering the floor above. There are multiple building codes in the world that have a specific height for this vertical separation from floor to floor. 914 is usually the magic number, which is used in the US, Canada, few countries in Asia Pacific, etc. This is to ensure that you have at least a minimum of 1 hour for the fire to spread from one floor to the next from the exterior of the curtain wall. So just to show you how leapfrog effect happens, this is a 3D model or a simulation. So a lot of architects love floor-to-floor glazing. They don't like having the spandrel panel because everyone wants to see continuous glass on the external. So when you have that, you have a fire which you cannot stop. Everyone understands that. Once it reaches the flashover stage, the glass is going to break open, which is because it's non-fire rated. You cannot stop that from happening. Once this happens, the fire is already on the outside of your building and is going to enter back into your building. This was going to happen within minutes if you do not have a spandrel panel separation, and this is governed by building codes. What I understand is in the UK, these there is no specific spandrel height that is mentioned, but where I am based in UAE, for example, you have a spandrel height of 914 mm, which is mandated by the UAE Fire and Life Safety Code. So let's talk about the materials that are used in passive fire protection, specifically for curtain wall constructions and for cavity barriers. Stone mineral wool, or as most people know it, rock wool, is a common product that is used in passive fire protection. Why are these popular? It's because they're very good in fire, number one. Number two, they also have additional properties such as vapor permeability, acoustic properties, dimensional stability. That's the flag of Wales, where our factory is based, to be fair. That's cut just to show it can do any intricate cuts and crevices. So if you have curved facades, inclined facades, don't worry about it. Stone mineral wool can help you. But that said, all stone mineral wool is not the same. Stone mineral wool has many material properties such as fiber diameter, fiber length, binder content, etc., which is part of it, which it has the maximum temperature that it can retain or that it can accommodate. Along with that, it also talks about, it also, let's say, leads to the shrinkage in a fire scenario, because if you have a lot of binder content, then the material is going to shrink in a fire scenario, and you don't want that for a fire stop. So you have to ensure that what you're using is tested and fit for purpose. Curtain wall, because it's non-load bearing, and in a pressure or wind or thermal scenario, it's going to move. It's going to move in and out. That is why you have the gap between your floor slab and your curtain wall. It's important, like I said, for your fire stop to accommodate this movement. Mineral wool is usually manufactured in the horizontal orientation, with the fibers in the horizontal orientation, or stone mineral wool. If the fibers are installed in the horizontal orientation, then your product cannot accommodate the movement, and your curtain wall, well, basically it will move still, but your fire stop will get damaged. So it's important for your fire stop to have vertical orientation fibers within the fire stop when it's installed. Now, how does that work? So this is how the product will accommodate movement. Now, this is part of the EAD, which is present within ETAG 026, which was there previously. I'm sorry about that. So this specific test was done for 500 cycles at 30 cycles per minute. And the product, it's important to accommodate the movement, and after, then perform in a fire. So again, this is fundamentals of fire performance of passive fire protection, resistance to fire and reaction to fire. So reaction to fire is the inherent property of a product itself on how it behaves in a fire scenario. And resistance to fire is to work as a system. So if a fire happens in this building, how long is that door going to contain the fire? And most usually, in terms of resistance to fire, it is categorized for fire stops as integrity and insulation, because fire stop is a non-load bearing element, so it cannot have a stability feature, or you don't expect someone to go and literally stamp on it. Because I'm looking at fire protection for curtain walls from a global perspective, I wanted to highlight all the different codes which are there around the globe and the test standards that they follow as well. So you will notice two test standards which are quite common, which is ASTM E2307, which is an American test standard, and EN 1364 Part 4. Now, these are the two most popular test standards for curtain wall constructions. EN 1364 Part 4 is what is used in the UK, is what I've understood. And again, this is in the US, where they use an American test standard called ASTM E2307. Third-party certification is something that we stand by. We want to ensure that what we do has a continuous process, is a continuation evaluation process, and not just one. We have multiple people from all over the world coming and assessing us, certification bodies from Korea, US, Europe, everywhere. So we want to make sure what we manufacture is what is tested, and there is a continuous assessment process, a quality check for that as well. And we don't want to be the ones that say that, yes, we are good. We want other people to say, yes, Siderise is good. So that's why we make sure that we have third-party certification for our solutions. Historically, BS 476, EN 1366 Part 4, UL 2079, they're all linear joint test standards, and these were the tests that were used for perimeter fire stops. However, this does not include or have a non-fire rated aluminium curtain wall. These are between two fire rated elements, and this does not simulate the curtain wall movement that it will encounter in a fire scenario. Because a non-fire rated aluminium is going to deflect, it's going to buckle, it's going to, the flow slab is also going to deflect towards a fire in a pressurized scenario. So the two test standards that are globally present, which are also present in a lot of building codes, is ASTM E2307 and EN 1364 Part 4. So ASTM E2307 is done in an ISMA test apparatus. It's an intermediate scale multi-story test apparatus. where it's the same apparatus in which an NFPA 285 is done for cladding assembly tests, if anyone is familiar with that. So basically you have an external curtain wall and you have the perimeter fire stop installed between the floor and the curtain wall, and the test only assesses the perimeter fire stop. What the test standard does is you have an internal fire and it simulates the fire breaking out of a window and impinging on the exterior of the curtain wall as well. So you have two fire sources, inside and outside. And the secondary fire starts or is initiated by the test lab after the first 5 minutes of the test commencing. So this is the ASTM E2307 test standard. It's an open furnace, non-pressurized test standard. The second test standard is EN1364 Part 4, which is a closed furnace pressurized test, where you have your perimeter barrier installed between the flow slab and your spandrel. Because of the positive pressure of 20 Pascal, which is present within the furnace, the flow slab is going to deflect towards your fire, to the furnace. Your curtain wall is also going to deflect in and out, depending on, well, the test to be fair. We've had both scenarios happen. A lot of people have asked which standard is better. I don't think we're the best judge to say that, but what I would say is go for someone that has tested and got certification to both the test standards, because they're both quite different in its own way. So I'm going to sign off for the curtain wall section by saying use what is tested and certified in terms of both a perimeter barrier and a spandrel panel construction, and also ensure that what you have can withstand fire for 2 hours as a full surface. There's no point if your spandrel panel is not protected and it's going to collapse and all you have is a ring of perimeter barrier which is around the building. So with that, I'm going to go to the next section, which is probably the elephant in the room, cavity barriers for cladding constructions, for external cladding solutions. We've had multiple fires happen around the world. So the video on the left is a video from Turkey, Istanbul, called Polar Tower, where the entire cladding elevation completely burnt away. And the curtain wall section on the left was protected because there was compartmentation between the curtain wall and the cladding zones. This video in the center, please stay focused. It started on the ground floor, and you should see how fast it rises up. And the video on the right is from the Dubai. It's from the Address Hotel. It happened on the New Year's Eve of 2015, which is when the codes in UAE changed and for the better. So I'll just forward the video. Hopefully it works. It didn't. Maybe now. So it started on the ground floor, and within a minute, and let's go to, a minute and 45 seconds, the fires reached the roof of the building. So obviously no one's got time to evacuate, and people are trapped in the building. So why does this happen? Yes, the entire cladding system is combustible, but other than that, there's also something called as the stack effect, which someone raised before in the room, or the chimney effect, as some people call it as well, which aid the fire, which basically the fire feeds on the fuel or the oxygen within the chimney behind the cladding assembly, and it rises up the cavity. So this is the video I stole from LinkedIn, to be fair, where a fire, as soon as the fire is enclosed within a plastic tube, you can see how it rises even above the firefighter, and that's within seconds. So even if you have non-combustible cladding, it's important to ensure that the cavity behind the cladding assembly is compartmented using cavity barriers or any such system that you prefer. So why are rain screen facades important? Rain screen facades are important because with development in architecture and construction, you require sustainable facades. And it was mentioned today morning that that's one of the buzzwords that are currently being used as well. So with sustainable facades, people want to ensure that circulation of air is present, you have drainage of moisture, rainwater, etc. that happens. But this also has a fire hazard that is present within this construction. So with that in place, what do you do, or how do you ensure that in a fire scenario this works? We could not install fire stops as we did for curtain walls, where we compress the fire stop between a flow slab and a curtain wall scenario, as this would stop the ventilation from happening. So this introduced a dilemma because we needed to have ventilation, but in a fire scenario, this cavity needed to be blocked off as well. So we had a cavity barrier with an intumescent on the leading edge or towards the rear of the cladding panel, and this would allow for the drainage to take place and for moisture to drain through, for ventilation to take place as well. In a fire scenario, however, the intumescent would expand. The intumescent roughly expands around 130 to 140 degrees Celsius, and it would close off the cavity, ensuring that fire does not spread up the cavity, causing a chimney effect. That being said, global codes around the world, while yes, you do require cavity barriers, a cavity barrier alone is never going to stop fire from spreading. You need to ensure that as a full system, what you have is tested and is fit for purpose. So if you look at the system section for cladding system test standards, NFPA 285 and BS 8414 are probably the most popular test standards. BS 8414 is obviously very popular here as well, is what is used worldwide to ensure that the entire cladding assembly is fit for purpose and the fire does not spread on the exterior and within the cavity as well. The NFPA 285 is also reflected in the US, and in Canada they use a test standard called ULC S134. This is basically an extract from the approved document B itself, where they say the locations of cavity barriers where it's required, where you require cavity barriers at every floor horizontally, vertically at 20 meters, and at an edge of an elevation. And you also require it around openings, so such as doors or windows, etc. So in a fire scenario, when your window's pane breaks open, your cavity barriers around the window is going to act as your first line of defense. So how are cavity barriers tested? So there is a test standard currently in a development phase with the EN called the 1364 Part 6. It's only been in the development stage for 7 years, so probably a couple of years more and we'll have it out. But yeah, so the standard is ASFP TGD 19, where you have the cavity barrier which is present, the intumescent, you will have a gap open, you'll have a thermocouple which is present above the opening as well. The gap should close within the first 5 minutes of the test commencement, and that's as per the standard. If it does not close within the first 5 minutes, then the test is a failure. And you measure as a normal fire resistance test standard integrity and insulation parameters for the test. You have the option of including thermal insulation within the test as well. So you can test, say, with phenolic as well as a worst case scenario, or with stone wool and a best case scenario to ensure that you get your required test result. But that will be mentioned in your third-party certification and your test report. So make sure to ask for that. So in terms of system testing, we mentioned 2 test standards of NFPA 285 and BS 8414. I'm going to kick off with NFPA 285. So this is a single wall test. It's the same test apparatus as an ASTM E2307. You have thermocouples all along the test apparatus, but what is important is this specific line where the failure is mentioned or measured. It's 1000 degree Fahrenheit, which I think is roughly around 600 and something degrees Celsius. So that's your failure criteria, and this is present on the exterior of the cladding panel and also within the cavity as well. So this was a test which we did in a lab in Dubai called Thomas Bell Wright. They are from the same manufacturer, but it was 2 different tests. One test passed and one failed. What was important was the first test had both of them are terracotta tiles. So the terracotta is a non-combustible panel, but the orientation of the panels was vertical, and on the second test they changed it to horizontal. And also they included cavity barriers in the second test as well. The initial test, once the first tile broke open, the fire entered the cavity and all the panels just collapsed because the aluminium construction of which was supporting the tiles just collapsed. As we mentioned earlier, it loses its integrity at around 350 degrees Celsius. But in the second test, even though the first panel broke open, I'm not sure if it's clear enough, but if the first panel broke open, but because you had cavity barriers, it restricted the fire from spreading within the cavity and ensuring that the test had a pass. Similarly, BS 8414, the failure criteria is on the second story level where you have a failure of 600 degrees Celsius both inside and outside the cavity, which is present for the cladding panel. That's the failure criteria in terms of temperature. I'm sure everyone is well versed with this after the Grenfell fire now. I'm going to sign off. This is my last slide. I didn't want to focus on any specific solution of Siderise or anything. What I want to say is we need to have a balanced approach in terms of fire safety. So where Compartmentation for passive fire protection is done along with active fire protection and suppression systems for and detection as well. So it needs to be a balanced approach. One should not be preferred over the other. There's a lot of building codes that give you exemptions saying if you have a suppression system, then you don't need passive fire systems. Also vice versa as well, where some people say that if you have passive fire protection, you don't need detection. For me, it doesn't make sense. You need to have all of them in let's say an equal proportion or a ratio where you make sure that you have a balanced approach. One thing that I will say is we need to make sure that this is influenced or this is enforced in the design stage itself. A lot of people come saying after 60% of the building is done, now what can I do to make sure that it's fire safe? There's nothing you can do. Whatever you do will be half-hearted or half-measured. So you have to make sure that this is implemented in the design phase, and with the design and the architects itself, we need to make sure that this is a practice that is followed. That's it from me. Thank you.